Okay. So today, as I said, we will be, continue with the modeling. If you remember this three circle which I'm putting, where the differential equation model, a transfer function model, and state space. In the past few lectures, we were, doing this process. From transfer function, we are going to the state space. And we have said we will be, having many, state space for the same transfer function. The same thing from differential equation. Of course, from differential equation to transfer function, you can go back and forth. What we want to do today is to go in this direction. Okay. We also have done this direction by using the signal flow graph, but today we are going to have a formula that relate the output to the input. That's basically, we have y of s, okay, equal to, Shabab, if you excuse me, I have a problem. There is a huge fly in my office and I don't know what to do with it. Okay, sorry.
You can see it, Doctor.
يا الله، هذا شو اليوم ما شاء الله المكتب حقي مليان يعني حشرة بتذلك يعني.
سبحان الله.
اوكي، سبحان الله فعلا.
الله سبحانه وتعالى يقول: ومن يسلبهم الذباب شيئا لا يستنقذوه منه ضعف الطالب والمطلوب.
سبحان الله. سبحان الله فعلا. So today we would like to obtain a relationship. If you have the state space, the quadruple A, B, C, and D, you would like to obtain a relationship that you would like to obtain the transfer function G of S, which relates U of S to Y of S. So what we want to do today, as I said, directly from A, B, C, and D, we would like to find transfer function. In the past lecture, we did, if we have differential state space, you do the signal flow graph, and then, you can find the transfer function. Today, we would like to give a formula, okay? And we are going to see this process is unique, that given A, B, C, D, we will have only one transfer function. So if I want to establish this relation, starting from this differential equation, what do I do?
Yes, basically we have established the previous relation between the matrix A and matrix B and matrix C and the coefficients of transfer function.
That's correct.
Right, so we can go from that. For example, if it's in a canonical form, we know exactly that the last row in the matrix A will be basically the the minus of the coefficients in a reverse order.
Very good.
From left to right. So we can go this way, yeah. But we have to know.
But okay, suppose what you are saying, Abdurrahman, if I have a transfer function in canonical form, or
yes,
the A, B, C, D in canonical form. Suppose I have a general matrix, so what do I do?
If you have what, Doctor, again?
Or I have multi-input, multi-output. That basically I have more than one input, more than one output. What you are saying is good, but look, this is differential equation. I would like to establish, okay, this is time domain. Let me go to the transform domain. So what is if you apply Laplace transform for the first equation, what do I get?
You get
S x dot, sorry, x
of S minus x of 0.
Initial condition.
Yes.
To A x of S plus B U of S. Look, the transfer function is the relation between U and Y. So I have to eliminate x. First of all, we are talking about transfer function. What will happen to the initial condition? Shabab, what will be the initial condition? Abdurrahman,
0.
connection problem, Abdurrahman. Yes? Zuhair?
We don't suppose initial conditions. We assume it to be 0.
Yeah, exactly. Assume x of 0 equal to 0. So I will have, and let me, I will have s, x of s, and let me bring a x of s to the other side. So minus a of s equal to b s. Now let me express x in terms of u. So let me take x out. Those are vectors and matrices. So minus a x of s equal b u of s. Can I put only s in here? S is scalar. So what do I have to do?
Multiply by identity I.
By identity such that the size of the I the same size of a.
This, doctor, resembles the eigenvalue problem.
Well, it is, yes. We will come to the eigenvalue. But in here, if I want to solve for x, I assume Si minus a is invertible.
Of course.
Not at the eigenvalue. So if this is invertible, then I can write x of s equal to Si minus a inverse b u of s.
And that's it.
So now let me go back. I have y of s equals, in the transform domain, x of s plus d u of s. Substitute. So this will be c si minus a inverse b u of s plus d u of s, which is equal to, let me take the u out, plus, sorry, d u of s. So what is g of s? Can you tell me?
Just between the parentheses.
Just the, just whatever in the bracket. So it's going to be c si minus a inverse b plus d. And this is valid for single input, single output, multi-input, multi-output, well, in canonical form, any general form, okay? So basically, if you have the quadruple A, B, C, D, you can find the transfer function. And the transfer function, okay, is unique. For the given A, B, C, D, I have only one transfer function. However, if I have transfer function, I could have infinitely many A, B, C, D. Any question here? Any question here, Shabab?
Doctor,
Fadal.
we just be careful when doing these things about the matrices. Like maybe some students will just commute between the variables. That will result in wrong calculations. Just to make a note.
Always, look, this is true. I mean, this is true. If you have the signal flow graph, what do you do also? If you have block diagram reduction, the possibility of, doing a mistake is something, and a procedure which you can use, which you can program, okay? This is, look, if you go to MATLAB, okay, there is a command, by the end of maybe next lecture, you will have the command that if you have transfer function, you can give a command to by MATLAB, it will give you the state space, or the other way around. If you have the state space, it could give you the transfer function. So the possibility of, I mean, doing a mistake is something, but what what we are doing in here, I don't know whether I understand your question. Your worry is what?
No, it's not a question, but a note that we should not commute between the variables. Commute, like
yes, you are right. No, those are matrices. No, you cannot exchange, for example, C and B, because I mean, for example, okay, as a matter of fact, we are going to come to, suppose I have a system. Let's say I have x1 dot equal to 3x1 plus 2x2 plus 3x3 plus u1, and x2 dot equal to 6x1 minus 5x2 minus x1 plus u2, and x3 dot equal to let's say minus x1 minus x2 minus x3 plus u1 plus u2, and I have y1 equal to let's say minus x1 plus x2, sorry, y2 equal to 5x1 plus 5x2, and y3, okay, will be, let's say, 5x1 plus 16x2. So how many output I have? How many outputs?
3 outputs.
How many inputs?
3 outputs. And
no, U1 and U2. That's all. 2 inputs.
هو جاني السؤال الاول خايس تاخرت فيه عشان ابغى احله ما ابغى اعدي عليه وقت.
يا
بعد دقائق او حتى اقل. فاذا كان عندك السؤال ذاك كان تقريبا كذا
يا محمد المايك فاتح.
او عندك
المايك فاتح يا سعد.
ايوه بالعكس
والله معنا.
Maybe انتبه الحين. Okay, so basically look, what you will have, okay, يعني you will have x dot equal a x, which is 3 by 3 in here, plus b 3 by 2, and y equal to cx, which is, okay, is going to be 3 by 3. So if you eliminate, what you are going to get, a matrix of 3 by 2. So definitely, back to your observation, I cannot, commute between A or between B and Si minus A inverse. This is not possible. Whenever you have matrices, you have to be careful in, you have to be careful in your calculation. This is also when you have, look, or if you take another example, if you have cascade, okay, G1, okay, and G2. If you have matrices, then you cannot, you cannot alternate between, you cannot commute between them, because it's not necessarily they are compatible. Okay, is that your question?
yes, understood.
Okay.
So if
Yes.
Si minus A is a very, very large matrix, and when we want to find the inverse using MATLAB, usually we use a function called M, which is referred inverse. But sometimes computationally, this will, be computationally hard or complex to find the inverse of a very, very large matrix. And sometimes it's not a sparse matrix. So, you know, but
there are, Abdurrahman, you are right. I mean, Abdurrahman, your mic is not.
This is problem that we will face.
Look, what you are saying is absolutely correct. Look, if you compare to the 70s and the 80s, okay, there is no MATLAB, there is no laptop, there was the mainframe computers. And people were using at that time, okay, we were using, you know, I mean, the analysis usually for very small system. Thing went after the 90, where MATLAB been introduced and more, you know, I mean, the computers become highly efficient, the power, I mean, in terms of the calculation. So yes, definitely, there is a problem, but, you know, I mean, as we move, I mean, generally speaking, okay, this is very, I mean, MATLAB is very useful tool to do the calculation. Well, I mean, in general, I mean, if you want to study anything, realistically speaking, we are, you know, the dimension is reasonable, okay? But definitely, I agree with you. There are certain cases, but at least, you know, what I'm saying in here, at least it is better, you know, even if you have 3x3 system. Now, in a moment, I will show you. 3x3 system, if you want to invert it by hand, it will be extremely difficult, okay? While in the computer, it will, the accuracy is extremely high and very fast. So, I mean,
Right.
we should not go to the extreme and we said, okay, so I'm not going to use it because, you know, there is a possibility if I go to very high. No, I agree. The sparse system and, you know, the competition, the computation is very hard. This is true. But generally speaking, as I said, for a realistic system, let's say 50 by 50, I don't think you will have any problem. Okay. Is there did I explain at least?
Yes, that's well said.
Okay, now let's take an example. Okay, in this example, okay, what we have a circuit, and we would like to obtain the state space first of all, and then apply the formula. I'm sure, you know, we have done it in the past by, you know, getting the state space and do the signal flow graph and get the, you know, transfer function. But today, no, we would like to, first of all, let's, you know, obtain the matrix representation and then apply the formula we have put. So the state space, okay, I have how many states I should have? How many states I should have?
2 would have.
Okay, so let me assume. Let's say VC is the first one. So if you apply KCL here, what do I have? I will have C dVC dt plus the current through the inductor
1 over L.
1 over L. No, just
لا قصدي على الفولتج يعني.
No, okay.
IL will be the same IL يعني.
No, I thought you said 1 over IL. It's not 1 over IL. Okay, equal to U or
ايه انا حسبت دكتور انه بنستخدم الفي سي 2 times.
So dVC dt equal to minus 1 over C IL plus 1 over CU. This is the first differential equation. The second one, we get it from KVL in here. So I will have L DIL dt plus R IL minus VC equal to 0. Any question here? Which means DIL dt equal to minus, okay, or plus, sorry, 1 over LVC minus R over LIL. This is the second differential equation. What about the output? What's the output equal to? What's the output will be?
IL multiplied by R.
Equal, okay, it's going to be R times IL. So we can put this one in a matrix format.
دكتور بس لحظة في سؤال هنا. أنا لما جت when you write the first equation, I thought about not using IL, but rather using 1 over L integration of VC dt.
Why, Abdurrahman, why do you do that?
يعني عشان يصير عندي one variable في
No, but
differential
wait.
equation.
Abdurrahman, you in the state variable model, we would like to have first order differential equation. So why should I go to
مضبوط. لأن لو صار كذا هيضطر عندنا يكون second order differential equation. صحيح.
Okay, so this is straightforward. What you are saying is correct. You could do it, but I mean, what I'm saying, you know, as if, you know, you want to go to the Dahran Mall, okay, rather than using the main entrance, you'll go to Aramco side and go to, you know, why should you do that? Okay, so it depends on the application, but this is basically okay. So if we, okay, so this is basically, if you put them in a matrix format, this is the A matrix, this is the B matrix, and this is the C matrix. There is no D matrix in here. When do we have a D matrix? When do you think we will have D matrix?
When we have the higher, when we take basically the steady state, and we have a value for the steady state.
No. The D matrix will come, look, from two situations. If you have transfer function where the system is, you know, just proper, that the numerator and denominator, they have the same degree. So in that case, you will have a D matrix. Or there is direct coupling between the input and the output. For example, suppose I have the following example. I have operation amplifier, let's say, in here. This is R and this is V out. Another R, and let's say I will have in here R and C, okay. This is, let's say, R, okay. And then this is VR, V input, VR. And I have a connection in here, let's say, R2 or Rx. So there is a direct link from the input to the output. If you have such a case, then you will be having, you know, if you have such a case, you will be having the D matrix. So D matrix means that I will have direct link from the input to the output. Okay? Now, back to our problem. So basically,
طبعا هنا دكتور يعني من ناحية simplicity احنا طبعا we are just learning يعني how can we go from one model to model, but we can just use the current divider rule and voltage divider rule if we want to with the Fourier you know S1 over SC and SL, and we can find the transfer function directly, right?
Yes, you can. What we are saying, look, at the beginning of the lecture, what I'm saying, the objective in this lecture in particular is if you have A, B, C, D, how can you get the transfer function? We show, well, as I said before, we can go either directly by, you know, if you want to find the transfer function, you can, you know, use the impedance. And here you have SL, and this is 1 over CS, and proceed. But what we are trying to do in here, how do I relate that? Because in many cases, especially in design, you would like to go back and forth between the transfer function and state space. So what we are doing in here, an alternative way, or if you have the ABCD, you can go directly and get the transfer function. And as you said, if you have a large system where you already have the matrices of the system, the ABCD of the system, you can, you know, it will be easier than using the signal flow graph. Also, when you have multi-input, multi-output, with the signal flow graph, it will get a little bit messy.
And the issue, Doctor, that we have to address when we go from the state space to the transfer function is that we will lose the initial condition. We will not be able to.
This is always true, because because the way we are defining transfer function is by setting the initial condition to 0. Yeah, this is true. But we are not violating what we have. I mean, for this circuit, if you do it directly, okay, or through the state space and again transfer function, you get the same transfer function. So it will be the same. We are not violating anything. So basically, if I want to use this one, so Si minus A, look, go back. This is A, this is B, and this is C. So Si minus A. So what is Si? What is the dimension of Si? Should be. What is the identity size?
2 by 2.
2 by 2.
So basically, if you do that, Si minus A is going to be S 1 over C minus 1 over L S R plus over L. Now I want to invert.
Yes.
How do you invert 2
في
by 2?
الماتلاب لازم يعني we have to define S as a variable, right? Or as
No, you don't.
using
No. In MATLAB, you just give A, B, C, D, and then give a. There will be. I will give you the command, and it will. No, you don't define anything. You just A, B, C, D. Your input A, B, C, D, and then your output transfer function.
as simple as that.
Okay.
As simple as that. And you just give them.
As simple as that. They program it because look, there is a program. Okay, now this is 2 by 2, so the inverse of Si minus A inverse equal 1 over determinant, which is the S times this one, and then minus the other diagonal, multiply by, you interchange as the diagonal element S R over L, and this is S, and in here I will change the sign only. Okay, 1 over C. Okay, this is the inverse.
Yes.
Now just multiply by the B and the C. If you do that, this is basically what you are going to get. Okay. Well, as I said, the state space representation is not limited to single input, single output. Suppose I have A, B, and C, where I have 2 input, 2 outputs. So what do you expect? What is the transfer function size? What is the transfer function? What is the size of the matrix of the transfer function? Remember, y equal G of S, U of S. So G of S relates the input to the output. How many input I have? 2
inputs, yeah.
And 2 outputs. What do you think the size of the G matrix will be?
It has to be 2 by 2.
Exactly, 2 by 2. It's going to be 2 by 2. Okay, well, okay, take Si minus A inverse. If you have, in general, the inverse of Si minus A inverse equal to adjunct of Si minus A over the determinant. I hope you know how to find the adjunct of a matrix or the inverse for more than
the adjacent.
Okay. So how do I get the first element? Okay, if you remember Si minus A inverse or Si minus A equal to S minus 1, 0, 0, S plus 4, minus 3, 1, 1, and S plus 2. So in order to get the first element, this element, well, you eliminate this row and this column and get the determinant of whatever left in your matrix, and that will be the first element or the cofactor. Then you alternate in the sign and continue. I assume you have taken the inversion of matrix in one of the courses. I don't know which course, but
actually, Doctor, there are multiple ways to take the inverse. So
well,
this particular way,
we are, you know, look,
yeah.
Yes, there are many methods. I totally agree. Use any method will help you to get the inverse. If you do that, then multiply by the C matrix, pre-multiply by the C matrix, post-multiply by the B matrix, and this is your transfer function. As we have said, it is a 2 by 2 transfer function. Any question here? Any question, Shabab? So let me wrap it. Basically, what we are saying, if you have the quadruple A, B, C, D, we can, you know, apply the formula, the transfer from G of S equal to C SI minus A inverse B plus D. Okay. Later on, we will, next lecture, inshallah, I will give you a command by using MATLAB to, you know, find the transfer function. Okay. Further.
If we have two outputs, the GS matrix will have two rows, right?
If you have two outputs, yes, exactly. Number of rows determined by the output, number of columns determined by the inputs. So basically, G will be, let's say, Q by P, where Y is a Q by 1 and U is P by 1. Okay?
صحيح مظبوط.
Shabab, let's stop in here because, you know, I want to give you a couple of minutes at least to be ready for the quiz.